Hello everyone, welcome to COMP3721. I'm Nevin Zhang, and I'll give you a brief recap of what we have learned for the second part of the course. Our course is about the mathematical study of computing machines, and it is circled around two fundamental problems: what is an algorithm, and what problems are solvable in principle and practice. We have previously learned about the deterministic finite automata and pushdown automata, which correspond to the regular language and context-free language, respectively. They are quite simple. You can regard them as a warm-up exercises for this part. So in part 2, we learn about the Turing machine and understand that an algorithm is a Turing machine that always holds. Thanks to the Turing machine, now we can adopt such a precise notion of an algorithm to formally prove that certain problems cannot be solved by any algorithm. Such problems are said to be undecidable or unsolvable. Note that we will discuss the efficiency problem in part 3 later. As an overview, part 2 can be divided into two topics. The first is the Turing machine's basic definition and some variants, which will be unified by the Church-Turing thesis. And like how a pushdown automaton corresponds to a context-free language, the Turing machine decides recursive language and semi-decides recursively enumerable language. By introducing the universal Turing machine, we can keep working on the decision problems and use induction to prove some problems are unsolvable in principle. The second half includes representatives of unsolvable problems, such as the halting problem, tiling problem, and many others. So first, Turing machine and corresponding language. A standard Turing machine has a look like the illustration here. It is an enhanced deterministic finite automaton with infinite input tape on the right side and the ability to write on the tape. Formally speaking, a Turing machine has unlimited and unrestricted memory and allows writing to tape and reading back the stored information on the tape. For each move, the Turing machine would read a symbol on the tape, move left or right, or stay still. Maybe write one symbol to the tape and change to the state in the finite control. Formally, it is defined by a quintuple with all possible states, alphabets, including the starting symbol, empty space, starting state, halting state, where it stops, and transition functions. The configuration concerns the current state, current tape contents, and the position of the control hand. Conventionally, we have the following assumptions for the starting symbol. So once read, it moves right, and it cannot be erased. It can never be written on the indicate left end of the tape. For convenience, in addition to a similar graphical representation like what we learned about pushdown automata, due to the complexity of Turing machines, we have another set of graphical representations where we decompose a TM into simple ones like the symbol writing machine and head moving machine and connect them. So how does it behave? It will start at the initial state of the first. While it halts, it reads symbol and simulates the operation of the corresponding machine. If it reaches the halting state of a component, it halts. We primarily focus on a Turing machine with two halting states, yes and no. For an input string W, the Turing machine will either halt or never halt, like fall in a loop forever. If it halts and outputs yes, we say that M accepts W. And conversely, if it halts and outputs no, we say M rejects W. And we denote the output of M as MW for a language L, which means a set of strings if M always only accepts its elements and rejects its complement. We call it a recursive language, and that N decides L. Consider the input and the output under this situation. It is like a function F mapping from the language L to the language. Here we call M computes F. When we reduce the requirement, if N always halts on elements from L and never stops for its complement, we call L a recursively enumerable language, and that M semi-decides L. There are several properties of the recursive language and RE language. They are both close under complementation, union, concatenation, and clean start. And recursive language is also close under intersection, while RE language is not. RE language is the superset of recursive language, and context-free language belongs to the recursive language. These results are derived from the delicate construction of Turing machines. And we may rely on several variants shown below to prove the aforementioned properties or address other problems. A multi-tape TM has more than one tape and a read or write head. Like this illustration, it has 3 tapes. Each transition might trigger read or write or move on all these tapes. For two-way infinite tape TM, the tape extends to the left as well, and the assumption for the starting triangle is eliminated. The random access TM is composed of some registers, a one-way tape, and a program counter. And the last representative is the non-deterministic TM, where there are several possibilities for one transition. However, although there are many different ways to define variants of TM, or say computational models, to make them easier to program, all of them are proved to provide no more power than the standard TM introduced before. We have the Church-Turing thesis that suggests that if some algorithm exists to carry out a computation, such as deciding a language or computing a function, then the same computation can also be carried out by a Turing machine. It is called a thesis because it cannot be formally proved. However, it has a near universal acceptance, and so far, no counterexample is found. All in all, the Church-Turing thesis characterizes the nature of computation. We can now claim with confidence that a problem is solvable only if it can be solved by a Turing machine. So let's move to the second part, unsolvable problems. The standard Turing machine is case by case. They are used to solve very specific problems, and we introduced the universal Turing machine to address the decidability problems. It is more generic in the sense that it takes both the Turing machine and the corresponding input string W as its input, and it can simulate M on W. You can view a universal Turing machine as a store program computer, which can compute anything computable. And each standalone individual Turing machine is a program, and the input strings are the data to programs. To formally define a universal Turing machine, we have some simple rules to convert a Turing machine into a string. So for each state, we put a symbol Q before their binary IDs. The initial state is always composed of zeros. And for symbols, we put an A before their binary IDs. So in this way, each transaction function is a quadruple like this. The second part is centered around the decision problems. It is a yes or no question in many instances. And solving this problem is to design the membership in the corresponding language. For instance, when we ask whether a graph G is connected, we are actually asking whether this graph belongs to the language of encodings, which encodes a connected graph. Record that a language is decidable if there is a TM that always holds that accepts the language. Correspondingly, the problem is decidable, or say solvable, if there is a TM that always holds that accepts the language. You may think that a yes or no question is so simple that it is too far away from our goal to define unsolvable problems. However, in fact, every computational problem is either equivalent to a decision problem or is at least as hard as some decision problem. Not all problems are decidable. In reality, most problems are undecidable. Intuitively, while solvable problems can be decided by a TM, which can be represented by strings and therefore countably infinite language are uncomfortably infinite, as we learned in part 1. So we have this rho inequality suggesting that there will be no one-one relationship between solvable problems and the pool of all problems. To prove a problem undecidable, we primarily use the reduction technique. There are 4 steps in total: reduce, assume, solve, and bang. To reduce a problem B to a problem A means to use the solution of A to solve B, as illustrated in these 2 circles. The key here is to find a proper non-undecidable problem B, which can be solved by designing an algorithm based on A with the assumption that A is decidable. Generally, in our formal proof, we'll omit step 0 and present our assumption and the contradiction. Remember to verify the algorithm we construct can actually decide the non-undecidable problem. We use the halting problem as an example to see how we apply the reduction technique to prove a real problem unsolvable. The halting problem goes like this. Given a random Turing machine M and a random input string W, does N halt on W? And accordingly, the language recognition problem is whether this language H in the title is decidable. Well, it would be great if such a question is solvable, especially for us programmers to debug. It's basically asking whether given a program M and W data, whether this code snippets shown here will print out halted. If it really exists, we are able to discover all subtle bugs that make our program never return on some inputs. Well, for mathematicians, virtually all conjectures can be transformed into a halting problem, like the famous Goldbach conjecture. We just want to know if we enumerate on all even numbers, whether there will be a counterexample. The halting problem is also the key for us to know whether recursively enumerable language is recursive, since we can see that H is an RE language because it is semi-decided by a universal Turing machine, which will halt when the input is in H. Recall the 4 steps. First, we reduce the problem to H1, where the Turing machine halts on itself. This is actually a non-recursive language. Then we pretend that H is recursive and derive a Turing machine image to decide H. So we can construct another image 1 to decide H1. For an input string W, it will write image on WW and halts when image halts. To verify it, if W is in H1, which means W is an encoding of a Turing machine and it halts on its encoding. Image will halt and same as image 1. When W is not in H1, which means it is not a valid encoding for a Turing machine, or it is an encoding, however, this machine does not halt on W. So as well, image will not halt and the same as image 1. So we come to the final step where a contradiction appears and breaks our assumption. In case you have forgotten, the fact that H1 is not decidable is proved by its complement is not recursively enumerable. The contradiction lies in the definition of the counter H1, shown on the right, and the existence of a Turing machine that semi-decides the counter H1. Apart from the halting problem, part 2 has introduced more undecidable problems here. So we denote L as the language semi-decided by the machine M. Does Lm equals to the empty set, or does Lm equals to all the languages? And does machine M1, N2 semi-decides the same language? Does the empty string belongs to the language semi-decided by M? Does the language regular, which corresponds to the Rice theorem? We will all prove that they are undecidable problems by constructing Turing machines and use the reduction technique. And there is another undecidable problem, the tiling problem. It is a combinatorial problem. We have some tiles with unlimited copies, and there is an adjacency rule declaring that only a certain pair of tiles may abut each other vertically or horizontally. The problem is that whether it is possible to tile the plane with specified tile place in the lower left-hand corner, follow the rules with the tiles at hand. Well, that's basically all for part 2. Here I connect the important concepts together. The Church-Turing thesis tells us that TMs are the most general computing devices, and so far there is no counterexample. A recursive language is decided by a Turing machine, and a recursively enumerable language is semi-decided by a Turing machine. We further leverage the universal Turing machine to attack the undecidability problem. By using the reduction technique, we are able to prove that the halting problem, the tiling problem, and many others or undecidable. So that's all. Thank you very much.